first assumption we have to make in order for this to work, I told you at the beginning of calc that anytime we are going to deal with a trig function, it had to be in radians in order for things to work. So if you see a sine theta or a cosine theta, we are just going to assume it's radians unless we are told otherwise. If it was in degrees, we know we could just convert it. How? Pi radian is equal to 180 degrees. So we could always use that conversion if it were given in the other form. But unless I tell you otherwise, we will assume that we are dealing with radians. All right, so just as a refresher, anytime we're talking about trig, it's good to review a couple pieces. So some of our common things, if I'm talking about degrees and radians, the most common angles, so 30 degrees is equal to 45 degrees, 60 degrees, 90. Okay. In terms of our trig functions, they are continuous everywhere they're defined. So for every number in their domain. Remember, sine and cosine, they're nice smooth curves. They keep going forever. When you get into any of the others, you do have some asymptotes to worry about. So those are not continuous everywhere. That is an important fact when we go into these derivatives, because a derivative is a limit, and we know in order for the limit to exist, the left and right hand pieces have to match up. So when they don't, the derivative isn't going to exist. This is something that we saw back in section 2.2. We worked it out then. We had a justification for it. It is something that we said after that point we could just assume we know this, and so that is still true. The limit as theta approaches 0 of sine theta over theta equals 1. I'm not going to go back into the whole why now because we have done it before, but that is something that we will just assume to be true and we will use periodically. So just in case you had forgotten that, I threw it back on here now. So let's say I wanted to find this limit. Can I just plug in my theta? No, because I'm asking when theta is 0 and we can't divide by 0. So we have to have some other option. So things that we've done before, like factoring and reducing, is that going to help here? No. What other strategies have we used?
Conjugate.
Okay, would that be an option here? Probably. Let's try it. Alright, so on the top, if I distribute, we get cosine squared theta minus 1. On the bottom, I'm just going to leave this as theta times cosine theta plus 1. Cosine squared theta minus 1. Does that equal anything? Okay, remember, sine squared theta plus cosine squared theta equals 1. So cosine squared minus 1 would be negative sine squared theta. Okay, at first glance, this really doesn't look like it helped us at all because I still have a 0 on the bottom. But I am going to rewrite this. I'm going to separate these. I'm going to, my negative sine squared theta, I'm going to separate it into a sine and a negative sine. Bottom, I'm going to pull apart the theta and the cosine theta plus 1. Do you guys agree that if I multiply this, I would get back to the previous line? Yeah, because when you multiply fractions, you just go straight across. Now, we could do the limit of each of these pieces separately. We have a theorem that tells us the limit as theta approaches 0 of sine theta over theta equals 1 times negative sine of 0 over cosine of 0 plus 1. What's the sine of 0?
Wait. Why is it 0 now?
Because theta is approaching 0.
Oh.
Sine of 0 is 0. What's cosine of 0? 1. This is legal because 0 divided by 2 is 0. And 1 times 0 is 0. Questions on how I got to that point? So, this is the next thing we can assume to be true. The limit as theta approaches 0 of cosine theta minus 1 over theta, in fact, equals 0. So my next question, I want to graph sine of x. We did this at the very beginning, like in the third section, I think. We had some of our trig review, and we graphed all of our trig functions. What does the graph of sine look like? Sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is negative 1, sine of 2 pi is 0. So there is my graph of sine. So now I want to take what we know about derivatives and try to draw its derivative. So we know that anywhere we have a maximum or minimum, what's my derivative going to be? 0. Because those are my horizontal tangent lines. Okay, this whole time my derivative was, or my function was increasing, so that means the derivative will be positive. From this whole point, my derivative is my function was decreasing, so the derivative will be. Okay, after here, my function's increasing, so the derivative is positive. Does that look like anything we've seen before?
X squared.
It does kind of look like a parabola, yeah. All right, let's keep going with it.
Oh, that's the cosecant.
You're close, but it's not cosecant.
Cosine.
This black one is my sine graph. If we kept continuing this orange one is actually my cosine graph. So let's see if we can use it. So we think, based on that graph, the derivative of sine might be cosine. Let's use the actual definition and see if it works. So the definition of a derivative is the limit as h approaches 0 f of x plus h. So in this case, it would be sine of x plus h minus f of x. So minus sine of x all over h. Does anybody have that trig paper I gave you at the beginning handy? There's a formula on it we need. Bam. All right, so on this, we have sum and difference formulas. When we have sine of x plus h, so the first one on here, sine of a plus b, it says it goes to what?
Sine of A times sine of B plus cosine A, cosine B. Oh, cosine B, cosine H.
So sine of the first times cosine of the second,
Yeah.
plus cosine of the first, sine of the second. All right. So far, it hasn't overly gotten better, has it? Let's break this apart. So, what if I take these? So sine x, cosine h. I'm gonna go ahead and take my minus sine theta with that. So I'm grouping these two together. Plus, we still have that middle one we haven't used yet. Now, is this something I would expect you to do on your own? No. But I'm trying to prove something. Instead of just telling you the derivative of sine is this, I'm trying to show you why it is using the definition. I've grouped these together intentionally. What do they both have in them? Sine. So let's factor out that sine x. Pulling that up, all of this. On this one, I'm going to just separate that cosine x off. Because we know with our limits, we could do the limit of each piece individually. Sine x, that doesn't have an h in it, so it's just like a constant in terms of our limit. The limit as h approaches 0 of cosine h minus 1 over h. What is that? That's equal to 0 from that theorem that we worked out at the beginning. So I get sine of x times 0 plus cosine of x times, what is the limit as h approaches 0 of sine h over h?
1.
1 from that very first piece. So we get 0 plus cosine x, which is cosine x. So, just like we predicted from the graph, the derivative of sine is cosine. So that is something you can now assume to be true. You don't have to prove it. It is what it is. But you do have to learn that. Unless you want to be stuck proving it on a test, you need to know that the derivative of sine is cosine. Let's do one problem with that, and then I'm going to stop for today. If I asked you to do this derivative, what would you have to do?
The product.
Right, because I have more than one x. So we have to treat it as x squared times sine x. So product rule, derivative of the first, derivative of x squared is 2x times the second plus the first, so x squared, derivative of the second. Derivative of sine x is cosine x. So it's just 2x sine x plus x squared cosine of x.